Hello new viewers and subscribers of this channel. In this video I will explain you how to sketch a Nyquist plot of a transfer function by hand. But before we start, let us provide an answer to the following important question. And the question is, what is the significance of Nyquist plots? Well, Nyquist plots are used to investigate the stability of dynamical systems. We create a Nyquist plot of an open loop system, and on the basis of this plot and how this plot looks like, we can evaluate the stability of the closed loop system. The purpose of this video is to teach you how to sketch a Nyquist plot by hand, and I will only focus on sketching procedure, and I will not talk how these plots are used to investigate the stability of systems. This will be a topic of my next video. Before I start, I have to mention the following. It took me a significant amount of time and planning to create this video. Consequently, I kindly ask you to subscribe and press the like button. Thank you very much. The focus of this video will be on sketching the Nyquist plot of the transfer function that you can see over here. This transfer function has a pole at 0 and another pole at s is equal to -2. And this transfer function can be an open loop model of a DC motor where we basically measure the position. Before I explain you how to sketch a Nyquist plot of this transfer function that you can see over here, let us first try to understand the global picture. Let us try to understand what is actually a Nyquist plot. Okay, so let's start. Let us see what happens with this transfer function when we substitute s by j omega, where j is basically imaginary unit, square root of -1, and omega is a real parameter that varies from -infinity to +infinity. Let this be a complex plane, and let this be a real part of S, and let this be an imaginary part of S. So when we say that S is equal to j omega, we are basically restricting ourselves to the imaginary axis. So for example, for omega 1, we obtain the point over here on the imaginary axis. Let us see now what happens with our transfer function t of j omega when we vary omega from -infinity to +infinity. So what we actually do, we take omega and we slide along this axis. We go upwards. For any value of omega, t of j omega is actually a complex number. To see that, you can simply substitute here j omega and you can obtain something like this. 1 over j omega multiplying j omega plus 2. Some of you might not see this immediately, but this expression itself is a complex number. You can see that by computing the real and imaginary part of this t of j omega. We can represent t of j omega in another complex plane where this will be real part of t of j omega, and this will be the imaginary part of t of j omega. So for any value of omega, we are basically mapping this complex plane into another point into another complex plane. So if I substitute here omega is equal to 1, I will obtain an expression over here. I can compute the real part and imaginary part of this complex number, and I can plot it over here. Now, as I vary omega along the imaginary axis in this complex plane, I will obtain a set of points in another complex plane. For example, if I take this value of omega, I will obtain, for example, a point over here. If I take this value of omega, I will obtain a point over here. If I take this value of omega, I will obtain a point over here. Then if I take this value of omega, I will obtain a point over here. And now if you densely vary omega along the imaginary axis, you will basically obtain a plot of points in another complex plane, in this complex plane. And this plot is nothing less than the Nyquist plot. So this is our Nyquist plot. And here I have to mention one very important fact. So when we go to minus infinity to plus infinity, and when we reach plus infinity, we basically draw half of a circle that goes from plus infinity to minus infinity in the clockwise direction. So this is how we actually vary our omega. We go from minus infinity to plus infinity along the imaginary axis, and then we draw a huge circle that encircles the right half of the complex plane, and we end at minus infinity. And for every point on this graph, we are trying to find a point on the graph over here, or the point in this complex plane that basically represents the real part of our transfer function and the imaginary part of our transfer function. Now that we understand the basic idea of the Nyquist plot, let us now try to construct the Nyquist plot. So here is our transfer function. Our transfer function T of S is 1 over S multiplying S plus 2. And the first step is to substitute S by j omega. So if we write T of j omega, we obtain something that looks like this. 1 over j omega multiplying j omega plus 2. And let us multiply the terms in the denominator. J omega times j omega is minus omega squared. J omega times 2 is nothing less than 2j omega. And let's take minus 1 outside our denominator. And if we do that, we can obtain something that looks like this. Omega squared minus 2j omega. The next step is to compute the real and imaginary parts of our complex number T of j omega. To compute the real and imaginary parts, we need to recall one basic rule from calculus. Now, if a and b are real numbers, then we have that a squared minus b squared is equal to a minus b multiplying a plus b. So let us use this rule to compute the real and imaginary parts of our T of j omega. So T of j omega is equal to minus 1 over omega squared minus 2j omega. And let us multiply this fraction by omega squared plus 2j omega divided by omega squared plus 2j omega. And as the result, we obtained in the numerator w squared plus 2j omega divided by w squared to the power 2 minus 2j omega to the second power. And we obtain something that looks like this. Omega to the power 4, and let's see what happens over here. 2j omega squared is 4, multiplying minus 1, multiplying omega squared, and since we have a minus over here, we obtain this expression, plus 4 omega squared. From this expression over here, we can immediately see the real and imaginary parts of our T of j omega. So the real part of T of j omega is actually minus omega squared divided by omega to the power 4 plus 4 omega squared. We can simplify this expression by dividing the numerator and the denominator by omega squared, and we obtain minus 1 over omega to the power 2 plus 4. And this is our real part. How about the imaginary part? Well, we can write the imaginary part as follows. So, imaginary part of t of j omega is equal to, let's see over here, it is nothing less than minus 2 omega divided by omega to the power 4 plus 4 omega squared. And we can basically simplify this expression by dividing the numerator and denominator by omega, and we obtain something that looks like this. 2 over omega to the power 3 plus 4 omega. Now that we have computed the real and imaginary parts of our t of j omega, we are ready to sketch the Nyquist plot. I will use a relatively simple and intuitive way of sketching the Nyquist plot. Of course, if you have a better way after practicing these problems, you can also use another way. However, I'm trying to stick to the method that I used as an undergraduate student. Okay, so let's start. The first step is to make a small table. So let us make a small table over here. And this table will have basically 3 rows and several columns. The first row will be basically omega values. The second row will be the real part of t of j omega. And the third row will be the imaginary part of t of j omega. And over here, we can just sketch our original complex plane. Here's the S, and this is basically real of S, better to say, and this is the imaginary of S. And as I mentioned in the beginning of the video, omega is varied from minus infinity to plus infinity. However, while sketching the Nyquist plot, you don't need to actually vary omega from minus infinity to plus infinity. You can start basically from 0, from positive values of omega, very small positive values of omega, and go to plus infinity. Why is that? Because as you will see later, the Nyquist plot is symmetric with respect to the imaginary axis. So whatever happens from 0 to plus infinity, you can simply mirror this part and you can obtain the values for minus infinity to 0. That is, when sketching the Nyquist plot, you sketch the Nyquist plot for omega varying from small positive values to infinity, and you simply mirror the plot in order to get the complete plot that basically shows you how the real and imaginary parts of t of j omega vary as omega varies from minus infinity to plus infinity. So let's see what happens when omega is small positive number. We represent small positive numbers by 0, and in the superscript you write plus sign. And let us sketch our plane for the Nyquist plot. This will be basically real part of t of j omega, and this will be the imaginary part of t of j omega. Okay, so when omega takes small positive values, let's see what happens with our real part. So real part is basically equal to minus 1 over 0 plus to the power 2 plus 4. And since this is approximately equal to 0, we basically have minus 1 over 4. So here we can write minus 1 over 4. Let's see what happens with the imaginary part. So the imaginary part becomes minus 1 over 0 plus to the power 3 plus 4 0 plus, and this is approximately equal to minus 1 over 0 plus, and this becomes minus infinity. So we basically obtained the first point. The first point has approximately the real part equal to 1 minus 1 over 4, and basically it is somewhere over here in minus infinity. So this point is when omega is equal to small positive value. So our Nyquist plot starts from here. Here we put an arrow to denote from where our Nyquist plot starts. Okay, so let's see how does our Nyquist plot behave for another value of omega. But before we proceed with the next stage of sketching the Nyquist plot, we should keep this table nicely populated. You can see that over here I didn't put the value for the imaginary part when omega is equal to small positive value, and we basically computed this part and it's equal to minus infinity. So try to keep this table nice and neat. When sketching the Nyquist plot, it is always a good practice to find the points for which real and imaginary parts are equal to 0. In our case, we can see that in the numerator of the real and imaginary parts we have constants. Consequently, real and imaginary parts are never equal to 0 for finite values of omega. Taking this thing into account, the next good point for which we can sketch the Nyquist plot is the point for which omega tends to plus infinity. So let's see the real part. So the real part is equal to minus 1 over infinity squared plus 4. And this is approximately equal to minus 1 over infinity squared. And this is basically equal to small negative number. Small negative numbers are represented by 0, and in a superscript we write a negative sign. How about the imaginary part? The imaginary part is equal to minus 1 over infinity to the power 3 plus 4 times infinity. And this is approximately equal to minus 1 over infinity to the power 3, since the infinity to the power 3 is much larger than 4 times infinity, and this is again a small negative number that we represent 0, and in the superscript we write the negative sign. So what do we see over here? We can see that when omega tends to plus infinity, both the real and imaginary parts of t of j omega tends to small negative numbers. So our graph will somehow look like this. And the value over here, that is the 0, will correspond to the point omega is equal to plus infinity. Here is an interesting analysis that you can use in order to more precisely sketch the Nyquist plot. You might ask me the following question. Why did you sketch a Nyquist plot like this, and why do you approach your basically 0 point from this side and instead of, for example, approaching from this side or in this way? Well, this is because when omega tends to infinity, the real part will always be larger than imaginary part. I see that by looking at these infinities in the denominator. Here for the real part I have minus 1 over infinity squared, and this number, although small, is still larger than the number minus 1 over infinity to the power 3, because infinity to the power 3 is much larger than infinity to the power 2. So I know that I somehow approach my 0 point like this and not like this. Okay, so this part of the Nyquist plot corresponds to the values of omega going from 0 plus to infinity. So what happens when omega goes from minus infinity to a small negative number? Well, you don't need to sketch the Nyquist plot for these values. You can simply mirror your Nyquist plot with respect to the real axis. So the Nyquist plot for omega going from minus infinity to a small negative number will look somehow like this. And of course, this will be an asymptote that the Nyquist plot will approach to for positive and negative small numbers. And here, the point over here is omega minus infinity, and this point over here is omega equal to a small negative number. Now, we have almost completed the sketch of the Nyquist plot except for one very important detail. We basically need to determine how we transition from this point to the point over here. That is, how we transition from omega is equal to 0 in the superscript minus to the point omega is equal to 0 in the superscript plus. Do we go this way, or maybe we go this way? And this path is very important for determining the stability of a dynamical system, as you will see in my next video, and consequently it's very important to determine this path properly. So how to determine this part? So let us go back and let us look how basically our omega is varying. So this is the imaginary part of S. And to sketch the Nyquist plot, we started from omega is equal to minus infinity. Then we went here close to 0. Then we went to omega is equal to plus infinity. However, as we encircle the 0 point, we can observe that our Nyquist plot explodes. That is, its magnitude goes to plus or minus infinity. And we have to be very careful while analyzing this transition through 0. So again, to recapitulate, we start from minus infinity. We are here. We go like this. Then we approach a very small negative value of omega. So we are approaching here. Then we need to somehow figure out how to go to this point over here. How our graph goes from here to here. Does it go this way, or does it go this way over here? Okay. So when we approach 0, we are not going to directly pass through 0. Instead, what we are going to do, we are going to encircle 0. So we are going to take a path that goes like this. We are going to start from minus infinity, and then when we approach 0 from a negative side, we are going to take a half of a circle, and we are going to avoid passing through 0 point, because we know that at the 0 point everything explodes, and then we are going to continue further. Now let us zoom in over here and let's see how to parameterize this basically path. So what we are going to do, we are going to introduce a complex number S over here, and we are going to write this complex number as epsilon times e to the power j theta, where basically epsilon is the magnitude and the theta is the angle. So when we start from here, theta is minus pi over 2. Over here, theta is 0. And over here, theta is pi over 2. Now, let us go back and let us substitute the values, these values of s into our original transfer function. Here I will erase this table since I don't need it anymore. And let us recall our transfer function. So our transfer function has this form. T of s is equal to 1 over s multiplying s plus 2. Okay. Now, t of epsilon e to j theta is nothing less than 1 over epsilon e to j theta multiplying epsilon e to j theta plus 2. So what happens over here is that we have 1 over epsilon square e to 2 j theta plus 2 times epsilon e to the power of j theta. Since epsilon is very small, the term over here goes to 0. So we can simply cancel this term over here. And I'm just going to do this. And this is approximately equal to 1 over 2 to the power 2 multiplying epsilon e to the power j theta. And finally, since epsilon is positive, we can represent this complex number like this. Now, let's look at the global picture. This complex number approximates the behavior of our Nyquist plot in the vicinity of omega is equal to 0. That is, it will somehow tell us how we transition from this point to this point over here. Let us see what happens. When theta is equal to minus pi over 2, basically, the phase of this complex function is minus pi over 2, that is, it's equal to pi over 2, that is, it's equal to 90 degrees. So everything matches perfectly. So the phase of the Nyquist plot over here is 90 degrees. So we are at the correct spot. Let's see the point over here. So the point over here should correspond this, and the phase of this complex number should be negative pi over 2. So since theta here is pi over 2, if we substitute the value over here, we obtain negative pi over 2, and that's nothing less than negative value. Now, how we transition will be actually determined by this point. So let's see what happens when theta is equal to 0. When theta is equal to 0, basically the phase of this complex number is equal to 0. So what happens is that when we go along this way, our theta goes from minus pi over 2 to 0, which means that in this graph, the phase goes from pi over 2 to 0. So we go in this direction. And this is how we encircle the plane, the complex plane, when transitioning from this point to this point over here. And this is a very important detail when sketching the Nyquist plot, and you should always be careful when making this analysis. So whenever your transfer function has a pole, you might see this behavior. The pole should be on the imaginary axis, and when the pole is on the imaginary axis, you will need to perform this analysis. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please subscribe and support my channel. Thank you very much and have a nice day.